Shall we continue? Okay, let us continue. So before the break, we looked at the equation for MLP, and we also looked at different activation functions that one could use for the input and out, so the hidden and output layers, right? And in the end, I was mentioning that we are going to talk about what kind of models, like what kind of functions can a neural network model. Like, so before we start thinking about how to train like how to learn the parameters. Okay, so what we're going to talk about now is what kind of functions can a neural network model. Okay, so what kind of functions can a neural network model? So let's start with some simple examples. Okay, so here I have a neural network architecture where each nonlinear basis function, sorry, nonlinear activation function here is a step function. Okay, a step function looks something like this. It is nonlinear, right? Now, for the first unit, the function looks like this. For the second unit, the function looks like this. Now, when you combine these things together in the output layer, right? So then you start getting some nonlinear decision boundary where anything that is here is one class, anything that is below is a different class. Is that clear? So with just a bunch of step function, like we're getting this nonlinear decision boundary. Okay. Similarly, we can also use sigmoid activation functions. Okay. So here I'm using 4 different sigmoid activation functions as my hidden units. So each of this sigmoid activation function is by themselves linear, right? Like sigmoid gives you a linear decision boundary. However, when you combine all these things together, you get a blob like this, right? Like, which is a more sophisticated nonlinear basis function. Is that clear? So in general, with a neural network, like you should be able to get as complex like decision boundary as possible. For example, here I have an example where there is this boundary between R1 and R2, right? And within R1 region, you see another decision boundary for R2, right? And within this, you see R1. So this is such a complex decision boundary. Okay. So in fact, it so happens that you can model almost any function that you can think of by using a single hidden layer neural network. Okay, so this is often quoted to the universal approximation theorem, okay, which was at least the first version of that was defined by Harnik in 1991. There are many versions of this approximation theorem. So the universal approximation theorem says a single hidden layer neural network with a linear output unit can approximate any continuous function arbitrarily well, given enough hidden units. Okay, so given enough hidden units is really the catch here. So provided you have enough hidden units, you can approximate any continuous function by using a single hidden layer neural network. Is that clear? Now, even though this sounds very attractive, right? Like, so it's not such a useful theory in the sense, this is kind of an existential statement. Okay, so it says that for any continuous function that you want to approximate, there exists a particular parameter configuration for a single hidden layer neural network that can solve this problem, right? But this gives you no clue about what learning algorithm to use, like how to learn these parameters. Okay, so this only tells that the neural network is expressive enough to learn any function well. However, it does not guide you how to do that, right? Like, so that's one of the major limitations. of this universal approximation theorem. The second major limitation here is really this catch about given enough hidden units. Okay, so it so happens that as the complexity of the problem grows, the number of hidden units required to solve the problem grows exponentially. Okay, so which makes it useless if you want to solve complex problems, right? I see a hand raised by Roman. Is that an old hand raise or a new one?
No, yes, I have a question.
Yeah.
When we say a linear output unit in this statement, does this mean that the output activation layer is a linear function?
Yes. Yes.
And
Because
if
well,
the,
so that is because like we're talking about regression, right? Like so if you're trying to approximate a continuous function, we're doing regression, so the output has to be linear now.
okay, but if the output activation function is a linear function, then the decision boundaries shouldn't be linear.
No, because the hidden layer is nonlinear.
Okay, so it's only when the hidden layer is linear that the output is like the decision boundary is linear.
When everything is linear, the decision bound is going to be linear. Okay, with nonlinear hidden layer, like it is almost like it's kind of like having some nonlinear basis functions followed by a linear model, which we know will give a nonlinear decision boundary, right?
Okay, okay.
Okay.
Thank you.
Any other question? Okay, so yeah, as I said, like even though it looks like a single hidden layer neural network is a universal approximator, in practice it's rarely true. Okay, so which brings us to this idea of many hidden layer neural networks. Okay, now here is an idea. So we know that just one projection, one hidden layer projection followed by nonlinearity, like followed by the output layer, right? It's a single hidden layer neural network idea, requires exponential number of units in the hidden layer to solve complex problems, right? So how about I go more nonlinear? Okay, so this is what I'm going to do. I'm going to take the input x, okay? I'm going to project it to some space. Let's just call it h1, okay? Now, instead of going for the classification layer, I'm going to do another round of projection. We're going to call this h2. I'm going to do another round of nonlinear projection. We're going to call this h3. And then we do the classification. Is that clear? So, like a cartoon explanation for what this kind of architecture can do is, let's say my input data looks something like this. Okay, it's a nonlinear classification problem, right? Like, so we have a bunch of crosses covering like circles inside, right? So the hope with having multiple nonlinear projection is each nonlinear projection is going to help us to separate the data a little bit. Okay, so for example, after the first nonlinear projection, the data could look something like this. Okay, so then after the second nonlinear projection, the data could look something like this. It's still a little bit nonlinear, right? Then after the third nonlinear projection, the data could look something like this, so that you can just draw a simple line that classifies the problem, like the data. Is that clear? So essentially, we are increasing the depth of the neural network so that we get much more expressive model. Okay, well, maybe much more expressive is not true. Even a single hidden layer neural network is expressive enough, right? Like, so it is just that with more non-linearities, like there's more chance for us to have a projection which is going to help us separate the data better. Is that clear? Any
I
question?
didn't I
Yeah.
didn't quite catch why use multiple hidden layer because
Okay.
we said earlier because we said that only one hidden layer can approximate every
Yes. Yeah, yeah. Well, that is what I'm trying to explain here. Like, so, yes, it is true that only single hidden layer can approximate anything well, right? But that actually requires having exponential number of hidden units. Okay, so the number of hidden units grows exponentially depending on the complexity of the problem. Okay, which is not feasible sometimes. You might require so many hidden units that you might start overfitting, or it's just simply not enough number of units if the problem is too complex, right? So which is why we go for the depth-based solution. Like, so the idea of depth-based solution is, instead of just increasing the width of the neural network by having a very large hidden layer, I'm increasing the depth. So the hope is I can just use 100 to 200 neurons in each hidden layer. Now, because this is a sequence of nonlinear projections, it's a very, like, it's a highly nonlinear process, right? Because you're doing a nonlinear projection followed by another nonlinear projection followed by another nonlinear projection. This is highly nonlinear.
Okay,
Is it?
so we instead of multiplying all the parameters with one hidden layer, we had them, and so it's this is why we have less parameters at the end.
Yeah, well, the hypothesis here is you could use lesser number of hyperparameters, like lesser number of parameters with a deeper neural network than a shallow neural network.
Okay. Mm.
Okay. Any other questions? Okay, so now let's write the mathematical equation for this multi-layer neural network, right? So we're going to assume that there are L layers just for abstraction. So like we have an L layer neural network. Okay, now for each layer K, okay, I'm going to assume that H0 of X is given by X, the input. Okay, so for each layer, the pre-activation is given by BK plus WK HK minus 1 of X. So then HK of X is given by G of AK of X. Okay, and you continue this for L times, right? So the final output is given by Y is equal to H L plus 1 of X, which is basically O of AL plus 1. Is it clear? Any question so far? Okay, so now we are going to talk about learning the parameters of neural network. Okay, so we have defined a simple single hidden layer neural network. We have also defined a multi-layer neural network, right? Like, so now the main question that we are going to study for the rest of this lecture is how to learn the parameters of this model. Okay, so learning the parameters of neural network. Okay,
Uh,
so
on the
yeah,
previous equation, was this h of k plus 1 or k minus 1?
HK. This is HK. So HK is a function of AK, which is a function of HK minus 1, right?
Is k minus 1, okay.
Yeah. Okay. So we're going to consider a simple MLP which has n input features and m output variables. Okay. And the model is going to be H is equal to G of W1 transpose X plus V1. Y is equal to O of W2 H plus B2. Okay, and we're going to assume that we have some training data, which is a bunch of xi ti. Okay, for I is equal to 1 to p. So I'm assuming there are p examples. Okay, I'm assuming there are p examples. And the error function here is given by 1 over 2 summation I is equal to 1 to p yi minus ti squared. Okay, so this is a setup. I have a simple MLP and I have some training set. I'm doing regression, right? And I have a least square error function. Okay, so how are we going to learn the parameters W1, B1, W2, B2, right? So in theory, the idea of gradient descent should just work here out of the box. Okay, because the whole model is differentiable, right? So why is it all differentiable? Like, so you have a linear projection followed by a differentiable activation function, followed by another linear projection, which is also differentiable, followed by another activation function, right? So everything is differentiable. So if you just use chain rule, then you can compute dou loss by dou W1, dou loss by dou B1, dou loss by dou W2, dou loss by dou B2, right? And then just use gradient descent. We're done, right? So the basic idea here is just to do gradient descent. Okay. So, however, when it comes to neural networks, there is an efficient way to do gradient descent, which is called backpropagation. Okay, backpropagation is basically an efficient way of implementing chain rule using dynamic programming. Is it clear? So backpropagation is just an implementation of chain rule. Okay, so our learning algorithm is still gradient descent. Backpropagation is not a learning algorithm. It is just a way to compute gradients. So once you compute gradients efficiently using backprop, then you're gonna use gradient descent. Is that clear? Okay, there's a question in the chat. So when the neural network has multiple layers, is the output function applied after each layer, or so the output function is just applied after the final one, right? Like, so if you look at this example, you go from X1 to H1 to H2 to H3, then you have the output layer. Is it clear? Okay. So we are going to discuss, okay, so DP is dynamic programming. So if you have done an algorithms course, you would have studied dynamic programming, right? If you're taking reinforcement learning in parallel, you would have seen dynamic programming there as well, right? It's basically an efficient way of solving problems for people who have not seen dynamic programming before. Okay. So now we are going to discuss backpropagation in detail, like how to implement it. Like, I think this is also part of your assignment 4, right? But one thing I want to highlight is, even though 10-15 years back people were implementing this manually, now there are a lot of packages that exist which helps you does this by yourself. Okay, so for example, there's PyTorch or JAX or TensorFlow, okay, which are all basically some sort of auto-diff packages, okay, which does automatic differentiation and computes the gradient for you. Like, you don't need to write like the equation for gradient manually. Is it clear? However, it's extremely important that you learn how to compute gradients, which is why we are focusing on this in the assignment. Okay, shall we continue? Any questions? Any questions so far? Okay, let us continue. So now I'm going to do gradient descent for this neural network architecture by using backpropagation. Okay, now to understand backpropagation, we are going to look at the computational graph that is created by this neural network. Okay, so to understand backpropagation, okay, so we are going to look at the computation graph. Okay, so given the input, which is, let's say, x1, x2, 1, all the way to xn1, right? Like, so I said there are n features, right? Like, there are n features, the n features in input and m features in output, right? So given this, right, for the current discussion, let's assume that there is some neural network architecture here. It doesn't really matter how the architecture looks like. All it matters is it gives you some output. The outputs are y11, y21, all the way to ym. Just call it I. Okay, ith example, just to make it more general. Is it clear? So this is my neural network. Like, so the neural network takes x1 to xn as input, and it is producing y1 to ym as output, right? Now, what I'm going to do now is to continue this computation graph all the way up to the error function. Okay. Now for y1, I'm going to compute the error as 1 over 2 y1i minus t1i the whole square. Okay, this is the error for y1i. For y2i, it's going to be 1 over 2 y2i minus t2i whole square, right? All the way to 1 over 2 ymi minus tmi the whole square. Okay, so for each output unit, I'm computing the error. Then I'm adding all the error. Okay, so I'm just adding all the error. And that is my total error for the ith example. Is that clear? Any questions so far? Now, once I start, okay, so this computation graph is interesting because it starts with the input x1 to xn, and it goes all the way to the error function. So it computes the y, then it computes the least square error, it adds all the least square error, right? Now, with this graph, I'm going to tell you a specific algorithm which will quite efficiently compute dou ei by dou w1, dou ei by dou w2, etc. Any gradient that you are interested in. Is it clear? Any questions so far? Okay, so now let's see how to do this. To understand how backpropagation works, so we are going to talk about derivatives of network functions, okay, using this idea of B diagrams. Okay, so what are B diagrams? Like, I'm going to represent each unit with the function and also the differentiation of the function. Okay, so for example, if I have a sigmoid function, right, sigma of wx plus b, right? So this can be represented as wx plus b is basically linear projection, right? Like, it's just addition. When I differentiate, I'm going to get 1. Okay, then we have the sigmoid function. When I differentiate the sigmoid function, I get sigma dash. Is it clear? So for each function, I'm basically representing the differentiation of the function in the left side. So that is what a B diagram is. Okay. Now, Typically, given a neural network, we are going to do a forward propagation first, then a back propagation, then we will take an SGD step. Okay, so the forward propagation and backward propagation together is going to compute the gradient. So once you have the gradient, then you will do the SGD step. Is it clear? Okay, so now let's try to do some really simple computation. Yeah,
I didn't understand the graph notation, or like I don't understand that part. Sorry.
okay, it will become more clear once I do some basic examples. Okay, so we're going to first look at 3 basic graph computations. Okay, it's going to make it easier for you. So the first case is function composition. Let's say I have a function y, which is basically f of g of x. Okay, so what does this mean? This means you are taking x, you're first applying function g, then you're applying function f, right? So the computation graph for this will look something like this. You start with x, you first compute g, then you compute f, then from that you get y. Is that clear? Now for every unit, I'm going to put the differentiation of that unit in the left box. So it's going to be g dash and f dash. Is this clear? Like, is this computation graph clear for f of g of x?
Yes, it's clear, but I don't understand why we do this. But I guess we'll.
Yeah.
we'll
Okay. So the y part is going to get clear soon. Okay. So why are we doing this? We are doing this because we are interested in coming up with some efficient way to compute the differentiation. Okay. Now, first of all, let's try to do the differentiation by hand, right? So given this y, can you tell me what is dou y by dou x? Let's do this manually. So given this y, what is dou y by dou x? Anyone? Yeah. Anyone? So there is some answer. Is it just f dash of g of x?
F dash G dash of x.
Yes, it's f dash g dash, right? So the answer is going to be f dash of g of x multiplied by g dash of x. It's a chain rule, right? Like, because it's f of g of x, you'll first differentiate f, then you will differentiate g. Is that clear? So that is the answer, right? Like, so now let me tell you why this graph is interesting. Okay, this graph is interesting because I can follow certain rules and get this answer in an automated way. Okay, so what is the rule? So the rule is to always put a number 1 here. Okay, and go backwards. Okay, so from here I go here, I'm going to multiply 1 with f dash, so I get f dash. So then I continue going here. I'm going to multiply f dash with whatever is there on the left side. So this becomes g dash f dash. Okay, so when I come out, I have g dash and f dash, which is basically same as dy by dx. Is that clear? So the reason why we are using this graphical formulation is I don't need to manually compute the gradient. I can just put a 1 here and follow the path and integrate the gradients on the way. I will get the final gradient. Is this clear? Like whoever was asking the question before?
yes, thank you.
Okay, so we'll do a few more examples. Then you will. Right now, it looks like a really simple example, right? Like, so I'm going to do 2-3 examples. Then you will see how general this idea is. Okay, so let's look at another case. This time I'm going to do function addition. Okay, so y is f1 of x plus f2 of x. Okay, now even before we take the graphical approach, can someone tell me what is dou y by dou x? What is dou y by dou x?
F1 dash plus F2 dash.
F1 dash plus F2 dash, right? So you have to look at this equation and compute the differentiation, right? Now let's see how to do this automatically using the function graph. So the graph for f1 of x plus f2 of x is going to look something like this. You take x, okay, you're feeding x to 2 units. The first unit is f1, second unit is f2, okay? So then you're adding them together to get f1 of x plus f2 of x. Is that clear? So when you differentiate f1, you're going to get f1 dash of x. When you differentiate f2, you're going to get f2 dash of x. So when you differentiate this particular thing with respect to f1 of x, you'll get 1. With respect to f2 of x, you'll get 1. Okay. Now this is my B diagram. Let's follow the same procedure as before. Like I'm going to put a 1 here. I'm going to put a 1 here. Now this 1 is going to travel through every path. Okay, so this 1 is traveling through this path, so it's get multiplied by 1. It's traveling through this path, it's getting multiplied by 1. So if you continue traveling this path, you will get multiplied by f1 dash of x. You continue traveling this path, you're going to get f2 dash of x, right? So whenever you combine this together, this becomes f1 dash of x plus f2 dash of x. Is it clear?
One question.
Yeah.
If we have f1 of jx and f2 of jx, does it, when we do the back propagation, does it converge back and then split, like because it's the same jx? Or does it like just separates into, just as we did in case 1, like f1 would be f then j and f2 would be f2 and j?
So what is jx? You mean f1 of, oh, you mean f1 of, oh, okay, you mean f1 of g of x, f2
Yeah,
of g
yeah,
of x.
if we have a composition.
Well, then this is going to, well, maybe let's just draw that diagram for you. So you want to do f1 of g of x plus f2 of g of x, right?
Yeah, exactly.
Is that right? Okay, so in this case, then you will start with x. You'll first compute g of x, right? So then that g of x will get fed to f1 and f2 functions. Then it will get added just like this, right? So
Okay, that's exactly what I wanted to know. Thanks a lot.
right, so you can work out the things. And the nice thing about this approach that I'm describing is even here, okay, let's actually do this. It's a good exercise. So like here you have a g dash, here you have f1 dash, f2 dash, right? So what would be the actual dou y by dou x? What would be the dou y by dou x?
First it would be
f dash times g dash, right?
yeah.
Plus f2 dash times g dash, right?
Yep.
When you say f1 dash is f1 dash of j of x.
Yes, yes. Yeah. Well, it's going to be too long to write the whole function. That's why I'm just putting it as f1 dash. F1 means f1 of g of x. Okay. Okay. So now I can actually get this answer in an automated way. Like I can just start with a 1 here. This one travels this way, it travels this way, right? It goes all the way here, it gets F1 dash, it goes all the way here, F2 dash, right? So then when it gets combined, it becomes F1 dash plus F2 dash, right? This combined thing gets multiplied with this. So this becomes G dash times F1 dash plus F2 dash, which is the same answer. Is that clear?
I just don't get the G dash of F1 dash and F2 dash.
Oh, that's because whatever data comes in, you multiply it with the left-hand side. That's what the algorithm is.
Oh, okay.
Okay, so that is what we have been doing in all the examples. Okay. Anyways, this was a combination of case 1 and case 2, right? Like, so now you already see that you can actually make complex functions. You will get gradients automated in an automated way. Okay. So the third case I want to talk about is weighted edges, because neural networks has weighted edges, right? So the edge has some weight. So let's say I have some equation like y is equal to wx. Can someone tell me what is dou y by dou x? Can someone tell me what is dou y by dou x? Just w, right? So let's see how to do that. Like, so you have x and you have wx. The weight in the edge is w. Okay. So whenever you have a weighted edge and you're doing backprop, you start with 1. When it travels through the weight, it gets multiplied by the weight. Is that clear? Any
You say we
questions?
start by 1 because the output of the
We always
neural
start with
network.
1. No, we always start with a 1 from the output.
Because
Okay.
the output is a real number.
No, it has nothing to do with that. Like, this is just the way to construct the gradient.
Okay.
Okay, now a bit of a non-trivial thing. I'm going to give you 2 minutes to think about this. Okay. Let me state the fact. I want you to think about it and get convinced that it is true. Okay. So what I want to argue is, if I use these 3 cases: function composition, function addition, and weighted edges, right? If I use these 3 types of operations, then I can implement an MLP, single layer or multi-layer, it doesn't matter, but any neural network, by just these 3 operations. Is that true or false? What if we have a product of functions? Well, I'm pretty sure you can represent that using computation graph as well. But for now, with just these function composition, addition, and weighted edges, I can represent a neural network. Do you agree? If you agree, then okay, at least some of you say yes, right? So think about it. You can draw an architecture like the backprop diagram architecture for an MLP. Okay, so if you can do that, then the benefit of doing that is I don't need to compute the gradients manually. I can just run the backprop, and it is going to give me the gradients that I'm looking for. Is that clear? This is the idea of backprop. Like, so you do forward propagation, but when you do forward propagation, you are also computing the differentiations, right? So then during the backward stage, you start from the output, you go backward, and you integrate the gradients. Is that clear? Now, I'm going to make the statement that backprop computes the derivative of the network function f with respect to the input x correctly. Okay. By the way, so far whatever I have described is computing dou y with respect to dou x, right? We are still not computing the gradient with respect to the parameters. We are going to do that soon, but for now we are computing the gradient with respect to the input x. Okay. So there is a question in the chat: do we store the gradients at each stage to update the weights? Yes. If you want to update the weights, you have to store the gradients for each node. Is that clear? That's a good observation. So far, we are still doing only dou y by dou x. Okay, we haven't started talking about how to do dou y by dou w, right? Even before reaching there, like I want to say that backprop actually computes the derivative dou f by dou x correctly. Okay, so I'm going to prove this statement. It's a very simple proof by induction. Okay, so we're going to prove by induction. So the base case I have already proved. All the three cases that we have seen, those are the base cases. Okay, so the base cases are what happens when units are in series, function like the function composition case, what happens when units are in parallel, which is the function addition case, and the weighted edges. Okay, now these are the base cases. I have already proved them. My inductive hypothesis is going to be the algorithm. I'm going to make this assumption that the algorithm works for any feed-forward neural network with n or fewer nodes. Okay, I'm going to assume that this already works for n or fewer nodes, and I'm going to make, and I'm basically going to prove that this works for n plus 1 nodes. Okay, so the induction step is going to be, if the algorithm works for n node network, then it will work for n plus 1 node network. Is that clear? So this is what I'm going to prove now. Like I'm actually going to prove this by picture. Okay, so instead of making mathematical arguments, it's actually easy to prove this by picture. So let's assume that I start with some input x and I have a network. It doesn't really matter what the architecture is, and let's say computes a bunch of functions, f1 of x, f2 of x, all the way to fm of x. Okay, and the final function f of x is given by some phi of w1 f1 of x plus w2 f2 of x up to wm fm of x. Okay, so there's w1 here, w2 here, wm here. It goes all the way to phi of s, p dash of s here, which is my f of s. Is that clear? Okay, so now we made this assumption that with up to n nodes, backpropagation works properly, and we are trying to prove that for n plus 1 node network, it is working properly, right? Now, if this is an n plus 1 node network, what can you say about the number of nodes in this subnetwork? Anyone? So I'm saying that this whole neural network architecture has n+1 nodes. Okay, so what can you say about the number of nodes in the green subnetwork? Any thoughts? So the overall network has n+1 nodes. Well, at least 2, yes. What else can you say? Can you, well, at least 2 is the lower bound, right? Like, so what is the upper bound? n-1, yes. So in general, it's going to be less than n or less than n+1. Is that true? So if the overall architecture has n+1 units, then the subnetwork is going to have less than n+1. Yes, right? So if the subnetwork has less than n+1 units, then based on our inductive hypothesis, we have already assumed that whenever I compute f1 dash of x, that is true. I can compute f1 dash of x. Similarly, I can compute f2 dash of x, right? I can actually do all these computations for each subnetwork because the subnetwork is less than n+1, right? So then I can use the backprop algorithm, which is basically to put a 1 here, and this 1 gets multiplied by phi dash of s, and it goes all the way here. It becomes f1 dash of x. Well, there's also w1, so this gets multiplied by w1 first. Multiply by w1, then the whole thing here, right? So if I write it, f dash of x is going to be phi dash of s times w1 f1 dash of x plus w2 f2 dash of x plus all the way to wm f1 dash of x. Okay, so this is what I would get by running backprop, and this is also actually the exact f dash of x for this particular function, right? So this is just a proof by picture that whenever I do dou f by dou x by using the backprop algorithm, it's going to be always the correct gradient. And the nice thing here is this algorithm is agnostic to what is there inside the architecture. You could use sigmoid activation function, you could use tanh activation function, you could have 2 layers, you could have 4 layers. Run this backprop, you're going to get the gradients computed. Is that clear? Any questions so far? So one thing to remember is, like, I still haven't talked about dou loss by dou w. Okay, so we are still differentiating with respect to the input x. However, in practice, we would always compute gradients with respect to the parameters, right? It's actually a very simple change in whatever we have discussed to do that. So we will do that maybe after the break. If there are no questions here, we can take a 10-minute break and then